Ever wish you had a peek at the universe's blueprints? You know, those fundamental laws that make everything tick?
Yeah.
Well, today's deep dive, we're taking a trip right to the edge of that frontier.
Oh, wow.
Talking about a huge discovery at the Large Hadron Collider.
The LHC.
Yeah, the LHC, that massive particle accelerator buried underground over in Europe.
Yeah, for sure.
So this is where they smash protons together.
At crazy speeds, right?
Crazy speeds. Basically like recreating the Big Bang and seeing what they can find. And find it. They did. They finally observed entanglement.
Really?
In a pair of top quarks.
Entanglement. So that's like,
It's that spooky action at a distance.
Right. Okay.
And this is a big deal. Even if you just like follow physics for fun.
Yeah. No, I can imagine. It's pretty out there. So quantum entanglement, it's like two particles become totally linked.
Intertwined.
Yeah. It's like their destinies are tied together.
Oh, wow.
No matter how far apart they are. Like you could measure one
Okay.
and instantly, boom, you know the state of the other one, even if they were like galaxies away.
So like if one is spinning up
The other one flips to spinning down.
instantly.
Like, how does that even...
Blows my mind.
It's just wild. And that's just like the tip of the iceberg, right?
Yeah.
The quantum world is so weird, but this is why it's massive.
Yeah.
They did it with top quarks.
The rock stars.
Yeah, like the heavyweights of the particle world.
They're literally the heaviest, right?
Yeah.
Of all the particles.
Literally the heaviest, most massive fundamental particle we know of.
Oh.
And that mass, right, it makes them super unstable.
Oh, okay.
They only exist for a fraction of a second, like a tiny fraction of a second, and then poof, gone. They decay into other particles.
And then try to study that.
I know. Imagine trying to study something that doesn't want to be studied, like that just vanishes immediately.
It's like trying to read a message written on a soap bubble before it pops.
Exactly. It's kind of wild, though, right? It's like because they disappear so fast, that's actually what makes them, I don't know, almost perfect for this.
What do you mean?
Well, think of it this way. They decay so quickly, there's just not enough time for anything to mess with them.
To mess with their
spin, their quantum information, doesn't have time to get all jumbled up, interacting with other stuff.
Oh, so it's like they're preserving a perfect little snapshot, right?
Yeah, exactly. It's like a message, right?
Okay.
Encoded right at the beginning. Boom, and they carry it with them, untouched until, poof, they're gone.
And so that makes them great for studying entanglement, you're saying?
Exactly, like a pristine sample or something.
But I'm still stuck on, like, how they actually saw this.
Yeah, it's pretty wild.
Like a billionth of a second, right? They invent some new camera, a quantum camera.
If only it were that easy, right? But the technology is pretty amazing. They use the ATLAS detector. It's one of these huge experiments at the LHC.
Oh, right. Yeah.
It's enormous, like a building-sized, super sensitive instrument to capture these tiny little particles.
I always imagine it like, I've seen pictures, obviously, but it's like trying to figure out how an entire symphony worked. But you've only got a few notes.
That's a great analogy. You're not wrong.
Yeah. Like scattered around after an explosion.
Yeah. The ATLA detector tracks everything that comes out of these collisions. And they're trying to reconstruct what happened, like step by step.
Okay. So in this case, they were looking specifically for the top quark.
The top quarks decay.
Right.
Looking for these specific particles, electrons, and muons.
Which are way, way lighter.
Right.
Than the top quark.
It's part of what happens when the top quark decays.
Oh, okay.
And here's where it gets cool, right?
Okay.
So there's electrons and muons.
Yeah.
They actually keep a little bit of information about the top quark's spin.
What? Really?
Yeah, it's like if you had like a firework and it spun a certain way before it exploded, so the way it explodes kind of tells you which way it was spinning before.
Oh, that's really cool. So by looking at how, like, the direction of the sparks in that analogy,
Exactly.
you can tell which way the firework, or in this case the top quark, was spinning.
Bang on. And they did this over and over, tons of times. And they looked to see if there was this connection between the spins.
Between the top quark and the antitop quark.
You got it.
Correct.
If the spins were, like, talking to each other, even though the quarks themselves were decaying, then boom, entanglement, right?
Okay, so they're separate.
Totally.
But still connected.
But still linked. It's wild.
So how do you measure that? How do you quantify the talking, I guess?
Okay, so get this. They use something called a D value. It's basically like a score for entanglement.
So like a higher score, more entangled, is that right?
Yeah. Well, actually, it's the opposite. Lower is more entangled. Oh, okay. Interesting.
Yeah, and there's a specific cutoff. Like if the D value gets below -1/3, then you know something's up. You know they're entangled.
Okay, so what do they find?
Okay, get this. They got negative 0.537.
Wow.
Way, way beyond that threshold.
So no question then, right?
Oh, no question.
Yeah, yeah.
It's a clear signal they're entangled. And listen, this is huge for a bunch of reasons, but one of the big ones.
Yeah.
It means we can use these top quarks.
It's like a tool.
Yeah. It's like we just got this brand new, super powerful microscope, but for the quantum world.
Wow. To study entanglement even more.
Exactly. Because we can see it so clearly with the top quarks, you know? It's like this perfect system to probe all these, like, fundamental mysteries. And, you know, we were talking earlier about things like quantum discord and...
the steering ellipsoid, yeah. The steering ellipsoid, exactly.
Right.
And this result is like a stepping stone to all that stuff.
So what could we do with that? I mean, it's hard to even imagine, I think, for people.
So imagine, right, instead of just knowing, okay, these particles, they're entangled.
Yeah.
We can actually measure, like, how much information they share.
Okay.
Like, how deep does that connection go?
Wow.
That's what quantum discord lets us do.
So it's not just like yes or no entangled. It's like degrees of entanglement.
Exactly. Isn't that wild? And then the steering ellipsoid, oh, man, that's even more out there. It's like, imagine you could map all the possible ways those entangled particles could be connected. All the different ways their fates could be tied together.
And this, like, shows us that.
We can visualize it.
Oh, wow.
It's like this window into the weirdness of the quantum world, you know?
Yeah.
And hopefully it gives us a deeper understanding of how reality actually works at that level.
Well, this has been incredible. We started with particles smashing together, and we've ended up, like, on the edge of reality itself.
That's the fun part.
Right. But that's physics, right?
Yeah.
That's what's so cool. It's like, you know, you start digging into these tiny little details, and you realize they connect to, like, the biggest, deepest questions.
It's all connected.
And on that note, you know, we've been talking about using these massive machines, these colliders, to study the smallest things in the universe.
Mm-hmm.
And it makes you wonder, what other big questions are out there? What other impossible things might we one day figure out? So until next time, keep asking those questions.
Yeah.
And stay curious.